Aaronson Lund from the University of Queensland, Australia. He will be talking about boson sampling, right?
It's not going to work for me, is it?
No, Australia is not the center of it.
Alright, it's time for a hack.
Okay, thank you.
Alright, is that okay? Brilliant. Alright, so I find myself again between a whole lot of physicists and dinner. So, I'm yet another talk at this workshop, which has been very interesting, but this talk is also about BS. I'm going to take a bit of a, this will be a bit like the antithesis to John's talk. John said that he didn't want to read Aaronson's paper, and I did. And so...
You wanted to? I can't believe that. I can believe you read it. I can't believe you wanted to read it.
Alright, you got me on a technicality there, yeah. Well, actually, once I got to page 29, I didn't really want to read it, actually. Anyway. Okay, cool.
It was all downhill after that.
Yeah. I'm going to trip over something here if I'm not careful. So. Right, so what I'm going to talk about, I'm going to spend sort of half of my time trying to get everyone on the same page about boson sampling. Hopefully. It'll probably be as clear as mud, but we'll see. Once I've done that, I'm going to talk about our results that we found about boson sampling. We're trying to shove Gaussian states into these things and see what happens, and see if the whole complexity argument stuff still works. So this was a collaboration between our group at the University of Queensland in our Centre for Quantum Computation and Communications Technology. We like really long names. And the University of Bristol, the Centre for Quantum Photonics there, where I spent a fair chunk of last year, and Terry Rudolph at Imperial College. So, all right. So, oh, and I haven't updated the title. The accepted to PRL has actually appeared, but anyway, I just haven't updated that. Okay. So. Right, so my rough overview is as I described it. I'm going to try and explain exactly what's going on, to try and, not in a computer science sense, but in a 30,000 feet kind of overview that hopefully will be a bit more digestible, but we'll see. It'll probably just either confuse you or cause a great deal of discussion, but we'll see what happens. But once I've done that, I will just talk about the original result a little bit about single photons, which for Aaronson and Arkipov, and then I'll talk about what we did with spontaneous parametric down-conversion sources and looked at that, and our result essentially is that the same thing happens there, the same hardness argument holds. And then interestingly, if you take parametric down-conversion and throw away one mode, you end up with things that look like thermal states. So sort of a natural extension of what we did, we ended up showing that the sampling problem for thermal states is easy. That, to physicists, will not be a surprise, but it has a sort of non-trivial computer science application, if you would, which sort of reverses the onus. So physicists are telling computer scientists what complexity classes things are. So it was a kind of interesting example. All right, here we go. So, all right, so the very broadly, and everyone's talked about this already, is the problem is essentially some linear scattering with bosons, and you have a certain number of them in a particular number of modes. They scatter linearly, and then you just look at the number of bosons coming out in each mode, and you just detect them. And of course, everyone here is talking about photons, right? And optical photons, you know, these things are nice. So normally we talk about this in the context of linear optics. and the number of modes has to be bigger than the number of photons. Yeah. So that's just so that you can fit in the size problem that you need. Right, so the problem is producing the samples from this device, which is the important part. So just to make sure I'm totally clear about that, what I'm describing, so what I did is I picked a random, this is a, what have I got, 5x2, 2x5 unitary. So what this describes is 2 photons going into 5 modes, and I picked the unitary that just randomly. And then what I've done is calculated the distribution from this thing when you put your 2 photons in and what the clicks that come out the other side are. So this graph here shows on the horizontal axis, you probably can't see it at the back, so they're way too small. But what they are the configurations. So the first column describes getting 2 photons in the first mode of your detectors. And then the next column is 2 photons in the second detector and none anywhere else, etc., etc. And then you got all your other possible combinations. And so from this unitary, which describes the linear scattering, you get this distribution. But that's not what you want to do. That's not what boson sampling is about. You don't need an apparatus that produces this distribution. What you actually want is something that produces samples from that distribution, which can be represented as some long list of results for trials in which you feed in these photons into this interferometer and measure what comes out of it. So an example trajectory would be like something like this matrix here. Okay, so that's what I mean by sampling. Okay, so here's just sort of a strange animation I mocked up. So what this is trying to represent is sampling. N at the top, which you probably can't see, is the number of samples. And you just plot out the frequency of what you've got and overlay it with the probability distribution. And after a certain period of time, you know, this thing will very slowly converge at the usual rate, the square root of n kind of error bars over time. And so it's not producing the distribution itself is way too much for what you actually need to do with boson sampling. What you want to do is just produce the samples. That's all you need to do. So this is the same problem, but I'm just animating it and showing you it converges. But this is nothing unusual. This is just sort of a standard thing that would come out of your experiment. All right. So there's sort of a two worlds view of this thing. So what you want to show is that the quantum thing is harder than the classical thing. And so you need to sort of define exactly what you're going to do. So you've got two algorithms. One's classical, and its inputs are going to be the number of modes and the number of photons, and the unitary matrix that describes the linear interaction. But also as part of the classical algorithm, there is no randomness really in classical algorithms. You need to input the random bits into the algorithm as well. So there's a huge source of randomness that is an input into your algorithm for the classical algorithm. And it produces at the output some sample, just like I showed you in the previous slide. But in the quantum case, there's inherent randomness in the algorithm, right? So you don't need these random bits. And it just produces samples from its inherent randomness that's coming out of it. So essentially these two things are very similar. It's just that in the quantum case, the randomness is built in. All right. And this is where, okay, one more slide before it gets really, really complicated. All right. So the result of Aaronson and Arkipov was just that the algorithm to produce the samples is hard for a classical computer in the sense that it's not in P. In fact, if you follow what they actually say, it's even bigger than that. It's not in this polynomial hierarchy, which I'll get to in a sec. So their proof follows a sort of proof by contradiction. If this was easy, so if you assumed it was easy, then this thing called the polynomial hierarchy collapse occurs. And I'll try and explain what this is a little bit. But you can think of it as sort of a weaker form of P equals NP. That's relative to some oracle, and yeah, but I'll give you sort of a rough sense of it in a minute. And the way it's done is by this approximate counting algorithm. And what it does is you can use the approximate counting algorithm to try and estimate the matrix permanence. So I'm going to use the next couple of slides to just try and explain that bullet point.
So if you're comparing to P equals NP, that's a decision problem.
Yeah.
But you haven't said what boson sampling is a decision problem.
Right.
So I can't make the comparison in my head.
I know. Yeah, that's right. Yeah. So yeah, that's right. Yeah. So I'm not sure what you want me to say.
That's a bad analogy. Keep going.
I want you to tell me why boson sampling is a decision problem.
It's not.
Or it's
No,
not,
no.
But then I don't. But then I don't know why it's a weaker form of P equals NP.
No. I'm saying that the meta strategy, the strategy that Aaronson and Arkipov used to show it was hard, is a weaker form of P equals NP. So they assume you have this oracle that outputs this thing, and you use that as part of the strategy to this polynomial hierarchy collapse. So that statement there is only there to sort of give you a sort of a hint as to what this polynomial hierarchy collapse means. That's all I'm trying to say.
But maybe if P is NP, that polynomial hierarchy collapse.
Yeah. Then they'd say it would collapse completely to the zero, the lowest level. And that's considered highly unlikely. But if you do it to the next level up, it's slightly more likely, but still not thought to happen. And then each level you go up, it's more and more plausible that it could be the case. All right, so let me try and get to the hard bit and see if I can confuse you all. Here we go. So what is approximate counting? Now, so approximate counting is saying if you're given some function on L bits, so the little notation there is saying strings of bits, the zeros and ones, of length L, and this function maps on those strings and just outputs one bit, 0 or 1. And approximate counting wants to estimate, if you sum up all possible inputs, what's the total of that sum, but you don't calculate it, you just want to approximate it. And you want to approximate it in the sense that you want to give it to within what they call multiplicative error, but you can think of it as like a percentage error. So it's quite a demanding requirement. So another way to say this is, I want to estimate how many ones the function outputs. Or equivalently, you can think of it as like there's a set, which is the set of inputs that the function, when applied to it, gives 1. And you want to estimate the size of this set. And so these are just slightly different ways to just say the same thing, but this size of the set is used later on. That's why I put it up here. So what you can sort of think about this is that the sort of size of the things going into this function is exponentially large. It's bits of length L. So there's 2 to the L possible inputs into this algorithm, into this function. And so if you want to estimate this thing to some constant percentage error, then it's going to be very difficult, because there could be a case where there's only one input that gives the output 1, and you need to be able to estimate that to within some error that you're given, some epsilon, in a percentage sense. So it's actually pretty clear that this algorithm is not in P. So here's a little few steps that's a bit confusing. So this algorithm can be solved by access to an oracle for hash collisions. So what an oracle is, some device that will just solve a problem in one step. And the problem that I'm saying you should solve is this hash collisions things, and special functions on the input. And it's not important to know the details of this strictly, but it gives you a flavour of what's going on here. So the next statement is going to be a bit crazy. So this is what you actually need to do. You've got this hash problem, and what you want to do is find a solution to all this stuff. So there's some random functions that map from L bits onto K, k bits where k is much smaller than L, and then you want to find elements of these functions, these h's, which are called hash functions, such that for any time that if the result of the functions is different, then the things that went into the functions were different as well. And so it's not, I don't want you to try and understand this straight off, but what this lets you do is if you can find the smallest possible value of k for which this statement is true, then it estimates the size of this set in an exponential sense, 2 to the k kind of sense. And the reason that works, you can think of it like the pigeonhole principle. If this k was 1, then, and this statement was true, then that means there must be only one element in the set, because there's no, you've got these functions and then there's no other way you can satisfy it. If it was 2, you go up there, you can find a certain number of functions, and then the elements, there's only sort of a certain number of ways that those elements can satisfy this statement. And so finding this thing, which would use an oracle, you've got to find these so-called hash collisions. And so that's why you need an access to an oracle to do this thing. And so that gives you an estimate of the size of this set. How many ones does this function output? And it does it in this exponential way, which lets you do this multiplicative error estimate. All right, that sounds a bit crazy, but what this crazy statement seems to, it seems a bit weird, but what you can do is show it can be written in a form of these bounded predicates. So there exists an x for all y, there exists a z, and then some state. And that's important because of this thing called the polynomial hierarchy, which if you were to, yeah, this is where you don't, so fair enough. So
about the collapse.
Yeah. So the first thing people usually see about this polynomial hierarchy is this thing about oracles. So you have these oracles which produce the outputs to these problems in one step, and then they talk about NP oracles and then oracles to access oracles, blah, 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 blah. But there's a totally equivalent way. In fact, the original way that it was written by this Stockmeyer was in this way of bounded quantifiers. So you write down some language, you write down some statement that a computer is meant to try and decide whether this statement is true or false. And you have all these variables that go into it, and then you put in these bounded quantifiers which alternate in this there exists and for all, blah, blah, blah. And this is the thing that defines this polynomial hierarchy. The polynomial bit comes about because the relationship must be polynomially computable. You must be able to decide it in an efficient way. And all the quantifiers must be polynomial in length, in the number of bits. But if you remember that the number of bits being polynomial doesn't mean that the size of the quantifier is polynomial, because it's the number of bits, 2 to the number of bits is the total number of things that goes into these quantifications. So that's actually exponentially big. Alright, so what you can show from this is that this approximate counting argument from the previous slide, where I had there exists and for all, and there exists, I had 3 of them, is contained in the 3rd level of this hierarchy. Alright, so, and there's this analogy with this other hierarchy from natural numbers, this arithmetic hierarchy. And there is a proof in that one that every time you add an extra quantifier, you get something more. You get a bigger set. And it's strictly bigger. But there's no proof for complexity classes.
It's only true for that. It's not true for the complexity classes, right?
No, that's right. There's no, for complexity classes, there's no proof like that. It's just sort of a belief that someone should be able to do this, but they just haven't, right? So it's expected that this also holds, that each level is distinct. Each time you add this up and you go more and more, it's always in a distinct set. So, all right, now back to boson sampling. Those 2 slides were pretty dense and probably very confusing, but at least it gives you lots of talking points, right? If you want to talk to me at dinner about it, or it could send you into a coma. That's your alternative. Right, okay, so we got, everyone's talked about this already. That in the boson sampling problem, you have this scattering thing, but it turns out that the probability of getting certain configurations is equal to these matrix permanence squared of the submatrices of the unitary. All right. So now what happens is you think of this algorithm where think of the classical algorithm that I was describing earlier, where you've got the input is this unitary. You've got the random bits that go in, lots and lots of randomness that goes into this algorithm, and then it outputs a sample. And what you want to do, you think of it like this, the approximate counting, you think of that whole thing as a function. There's all these bits going in and bits coming out, which are the sample. And you just find out which, you sort of say, there's a certain configuration that you're interested in. And that's a bit like saying you want to try and approximate you want to try and have this function and now the number of ones. The ones are the ones you're interested in. So you generate something like that, and it's the number of, you want to count the number of random bits that will generate the samples of some particular event. So like this one in this slide where all the ones are in the first mode, like all ones in the first n modes. So if you can estimate the proportion of the randomness that goes into this algorithm, that gives you that sample that you're interested in, which has a probability proportional to the permanent. Then you can make some estimate of this probability, which is this matrix permanent. So like the set that I talked about above, where I had this sigma set, which is the set of things that satisfy this function, it's like the types of random bits that go into the classical algorithm that give me the sample that I'm after. And so that gives me this multiplicative error estimate of the permanent. All right. But estimating the permanent, not calculating it, estimating it, in this multiplicative sense, is this sharp P hard problem. It's not in sharp P, but it can be mapped into sharp P. That's the sharp P hard part. And that class contains all levels of the polynomial hierarchy, with all those bounded quantifiers up to infinity. So, what this is saying...
Is the permanent sharp P hard or sharp P complete? Is it
it's not strictly sharp P because it gives you, it gives you some sort of, it's not an integer that it gives you. If you're in sharp P, you want to have a number. You want to count something. But what I'm giving you here is an estimate of the probability, which is not an integer, okay? And so that's the technical difference, that if it was in sharp P, it would be giving you an integer, but in this case it's not. So that's why it's sharp P hard, yeah. So that it's just a subtle difference, that's all. All right, so what this whole argument is saying, therefore, is that if you follow all these things through, that this sampling, if the sampling problem was easy, it would essentially be in this third level of the polynomial hierarchy. But then that third level must contain this sharp P hard thing, which contains everything in this polynomial hierarchy, and that's how this collapse occurs. And so that's the contradiction that I talked about originally. As I said, that's probably as clear as mud. Right. Okay, so the second huge part of Aaronson and Arkipov's paper, which I'm going to spend one slide on, is this thing called approximate sampling. So what I had been talking about up until now is exact sampling.
Are you going to talk about Gaussian states?
Yes. Okay. Am I running out of time?
I imagine so.
Really?
I'm not the
chair.
chairperson.
Huh?
Because we don't have a third speaker.
Oh, don't tell him that.
Yeah, but it's okay. Time-wise, it's okay. So go on, please.
Cool.
We're doomed.
All right. So approximate sampling. The only difference is that you allow deviations in the distribution. You don't have what I gave before is that you'd have to have your classical algorithm would have to exactly give the right probabilities of samples. And all that approximate sampling is about is that there's some wiggle room. There's an extra parameter that goes into the problem that is some percentage error that you're allowed. And even having that, you can follow the whole argument through still, and you still get into this hard regime. And the way it's done is to hide from the algorithm where you're doing this permanent estimation stuff. You do it, you build a matrix, you embed, so you've got to pick a submatrix somewhere to embed your problem, but you do it in a way that's random and hidden from the algorithm itself. So there's no way it can possibly know which configuration of ones and zeros contain the problem that you're trying to do the estimation of. And that's the argument, that's the critical part of it. And there's a few other things, there's a few other technical things, but that you need to show. But that's the critical part of the argument. Some people have talked about these already. Alright. And these are false, as it says in the book. A boson sampler can efficiently compute matrix permanence. No, it cannot. It cannot compute matrix permanence. Because remember, that was never the point of this argument. The point of this argument was to show it was hard, not that it could do these things. Okay? And when I say compute matrix permanence, I mean give me the answer by computing all the entries. You might think, oh, therefore it can estimate the matrix permanence, because that's what you talked about. No, it can't do that either. It does that in this third level of the polynomial hierarchy, which is not efficient unless p equals np or something like that. But it's not efficient. All right. So I got the two big ones out there. Jens has already talked about this. It's a problem that's outside this NP class. In fact, it's probably outside the entire polynomial hierarchy. So that is saying to you that it's not like a factoring algorithm. There is not an efficient checking way to check the whole thing.
So I'm already stuck because, okay, so I know what boson, actually, you write boson sampling as 2 words, but I always merge them into one to know what it means.
Oh, I see.
But then you write a boson sampler and you haven't defined it. So when you say
right at the start.
A boson sampler as a device,
Yes.
and then you're saying can be efficiently verified. So you're
No.
So,
These are false.
no, but it's not clear.
Why? It's clear. Disagree. It's clear. No?
I agree. It's clear to you. Keep going.
We can talk about this. This is good. All right. Another one was that hasn't been talked about, I don't think. But many people try and map onto this boson sampling problem in an efficient way. You don't necessarily need to have that. This this approximate counting argument estimates things within a particular multiplicative error on a set that's exponentially big. Growing that set by an exponential factor doesn't change the complexity. So you can tolerate exponential overheads, but you have to do it in the right way. There's a whole lot of caveats there. So that one's a bit more subtle. And this,
What kind of overhead are you talking about?
if you have some problem that's going to compute the boson sampling distribution, but in order to do it, it's an exponentially hard algorithm on top of that, you know, it's not polynomially equivalent, it's exponentially equivalent. So it has an exponential overhead, this other algorithm that you're thinking about. That you can sometimes use the hardness argument in that as well. But you just have to be careful. There's a lot of caveats. And it's just because of this thing that this thing is not in P. It's in NP to the NP to the NP.
Is it even a decision problem?
No.
Yeah, so, would it be in any decision problem complexity class?
No. That's a good point though. And the last one is almost certainly false.
Got any data on that?
It depends on it really depends on the party and definition of popular.
I don't think you want to go to a party where you become popular if you go sampling.
Okay. And
All right. So Gaussian state stuff. I can zip through this, and we're running out of time. So, but essentially, I've covered all the bases for this. So. This is what I think of as an anti-meme, if that's even a thing. So scientists seem to think the opposite to what most people think. If it ain't broke, then break it and see what happens. So in this case, we're just sticking other states into the original device. So the obvious thing to do would be parametric down conversion, because that's the current sort of sources of single photons that people have. And so you just set up a new device that
What is
has.
this reference for IOW?
In other words, when theory meets experiment.
I thought it was like Ian Wang.
No. So basically you want to ask yourself this question of this bigger problem where you have twice the number of modes. So you'll have a mode configuration output. The samples you're outputting are now twice as big. But you just want to ask yourself, is producing the samples from this distribution still hard? And you think that there might be a problem because if you have multiple parametric down conversion sources and you just wait and you trigger on single photons and you don't do any adaptation, which is like the figure that I showed, there's no adaptation in there, then there's going to be an exponential overhead. That doesn't necessarily matter. That was one of my points, that exponential overheads aren't necessarily bad. What you do need to do is make sure that the size of the set of things that you will take into your proof is not exponentially small. And so what you can find is that if you take these ends, I've got to rabble for a class here. So if you take
Yes,
your...
Barry, settle down in the front there.
I need a cane. So if you have M modes, 2M modes and M of these sources, and you wait for exactly n clicks, then you would usually expect an exponential overhead. But if you don't care where the clicks occur, then it's okay because you can tune the squeezing parameters such that you don't get an exponential scaling. So if you have some single probability producing a pair in a source of chi, then you can write down the probability of a single pair from m sources. You get some expression, and then you do it for n pairs from m sources, so that you're going to get n clicks on your heralding mode. Then you get some expression, and when you plot it out, you find that there's a competition between the exponential growth of the binomial coefficient and the exponential decay of the chi to the n term, and you get this bump. And the peak of the bump occurs at a particular value of chi, and the probability at that point scales as a square root, 1 over a square root of the number of photons. But the location of where those n clicks would have occurred is totally random. Okay. So what this is saying is that essentially this parametric down conversion setup is equivalent to the original thing where you're putting in photons just in totally random modes. You've just completely randomized where the inputs are going in. So does this matter? That any particular location has an exponentially small chance of being the right thing that you might want. But as I've just argued, if you're only waiting for those n photons, you just need a polynomial overhead. And that you know where those locations are because you had all these heralding modes and they tell you where the photons were. Yeah, so you get the probability with a permanent, just like before, but you get this exponential factor in front, which is the exponential factor that comes from the fact that there was a whole heap of other possible arrangements for the photons to go in. But it's not, it doesn't sort of change the complexity curve. It's not just some super exponential decay. And so you can argue a lot, and with a lot of appendices and a lot of proof, that this then is just as hard. But so I'm just giving you the overview of how the proof goes.
So is this the same as what they now call scattershot boson sampling?
I believe so.
Yeah.
And I would love to see who originated that term. Is it in the literature?
I think it was
Aaronson's
Aaronson's blog.
Aaronson blog, is it? Oh, okay.
No, it was Aaronson quoting someone from Oxford.
No, let me correct you.
I'll just get my popcorn.
So I have the emails to prove this, but Steve Kortamer actually started to call this start anywhere boson sampling.
Start anywhere.
Start anywhere, and then Scott proposed scattershot,
Yeah.
and Steve was happy with that.
The first time I saw it was in Aaronson's blog, and he didn't quote it,
Okay.
so I'm quoting him.
Okay. Interesting. Well, the origin of that is settled. Okay, cool. So, all right. So, how much time do I have?
10 minutes?
Minus 10 minutes, okay.
No, plus.
Oh.
Because according to the schedule, you have 20 minutes. It's the previous speaker will give
We don't
you
have to
10.
run 90 minutes.
No, we don't.
The whole point
Okay,
was to
so-
end early by deleting the last speaker.
Even,
But if you tell Austin
No,
there's
no,
an infinite amount of time.
even that is 5:30.
Okay.
Yeah.
All right.
So yeah. Well, we
You'll
just,
be glad to know there's only one more
But
slot.
that's okay.
Oh, okay.
But each slide required 10 or 15 minutes of arguing. So
Yeah, that's right. That's right. All right. So
first speaker finished good.
this sort of came out of when you have your parametric down conversion sources, and what you do is you just throw away one mode. You get something that looks like a single mode thermal state. It's just with the temperature that's determined by whatever the squeezing strength is of that parametric down conversion. So it was sort of natural. It came out of the maths of what we did. That there's you can sort of do this whole thing with thermal states just by sort of throwing away one arm, which is kind of curious. So what I'm doing now is I'm going to define a slightly changed problem where I'm going to, instead of injecting single photons into the first n modes, I'm going to inject thermal states of possibly different temperatures into all modes. And then I'm going to interact them with some arbitrary unitary linear interaction. And then I'm going to look at the probability of detecting one in every output of this device. All right, and what you find is that the probability of this thing detecting one everywhere is the permanent of a matrix, which is surprising. Okay, it's a permanent of a matrix, so it's going to have this same argument, right? Like this whole Aaronson and Arkipov argument. But it turns out there's a subtlety. So the matrix that you take is not an arbitrary unitary. It's not a submatrix of a unitary. What it is the matrix is some positive definite matrix whose decomposition is determined by the unitary and the temperatures of the thermal states that go in. So the eigenvalues are determined by the thermal states, the temperatures of the thermal states, and the unitary matrix which diagonalizes it is determined by the unitary. So that matrix is positive definite, and the permanent is of this positive definite matrix, which is not entirely trivial. You would think that maybe there's some funky result about the permanent of positive definite matrices. But there's not really. There's results about permanence of positive entry matrices, where all the entries are positive.
Non-negative.
Yeah, non-negative. But you can have a positive definite matrix which has negative entries. That's certainly possible. Complex entries. So it's not entirely a completely trivial thing. But the physics of this problem tells you that the thermal states have a completely positive p distribution, right? So they have this explanation in terms of randomness of coherent states going into the thermal states, and you can inject them into this interferometer. So you realize your thermal states as a random mixture of coherent states. Then you can propagate your coherent states easily through this linear optics unitary, because it's just a standard transformation of those classical field amplitudes. And then you can also, for each of those things, figure out a probability for all the detecting all ones. And so you can produce the samples using a p function that realizes the trajectories of these thermal states through this thing. So the sampling problem is in p.
Oh, stupid question. So in the same sense, you can efficiently sample in P,
yep,
but you will not be able to predict all probabilities, which you don't have to.
That's right.
You can't.
That's right.
Okay, good.
That's right. That's right. Yeah.
That's another of the fallacies, right? That you need to
But he can explicitly construct the output state, which means that it's...
I don't need to. No.
So you
you could.
Yeah.
That's also true.
Yeah.
It's Gaussian, yeah.
Yeah. But what you want to actually know is that you want to get the samples out, right? You want to get the samples after detecting in a non-Gaussian basis. That is the Fock basis here of all ones.
I guess my point is if you could efficiently construct the output state, then you can efficiently sample.
Not necessarily. No. Consider the case of putting in not thermal states, but pure squeeze states, so like single mode squeeze states. okay, Gaussian, okay, described by some covariance matrix. That covariance matrix, you just push it through the unitary by a symplectic map. You can then know exactly what the output state is with all its correlations, or it's totally Gaussian. So what's the probability of detecting in the Fock basis for that Gaussian state? So that's not efficient, right? It could, in fact, that would include our previous one with parametric down conversion. You could decompose that whole thing into inputs which had single mode squeezes and some big ass unitary, and then Fock state detection.
They all have the same squeezing angle. I think it's sufficient, but you're right.
Even if it's
different angles, that it's.
It's not clear. That's all I'm trying.
It's not clear yet.
I'm just trying to point out
Carl Caves' result.
Right. Okay. Okay. So there is an efficient classical sampling algorithm for this. Right. So does that mean it's efficient to estimate the matrix permanent of these positive determinations? No. But what it does say is that it must live in this third level of the polynomial hierarchy, which is smaller than this sharp P hard set.
What's the decision problem that lives in the third level of the polynomial hierarchy? What's it?
Can we talk about this afterwards? Yeah.
The point that you had one more slide was really not useless in terms of conserving.
No. All right. This is my last slide. It's a really good question that comes up quite a lot. So, what the hell is this good for? And at this stage, it's not super clear. And I think other people have said this. But it's clear that the message is that quantum physics is classically hard. And this has got implications for this extended Church-Turing thesis. Right? That's the message. That's pretty important. But, you know, most university students who do quantum mechanics will tell you it's hard. They're probably aware. So, perhaps the best approach is this paper that appeared on at the end of the year on the archive, is where they're trying to map these sampling problems into actual physical outputs of things that people are interested in. And in this case, it's the vibrational spectrum of molecules. And so this paper...
That's for Gusik's, the last one.
That's it, yeah.
I was refereeing this paper.
Oh, right. And you said it was great.
I did.
Oh, good.
He was referee on my paper on metrology, so we had
okay. So perhaps this is the approach. Where maybe the way to say this thing is useful is to say it maps onto physics problems that people are interested in and have been interested in for a long period of time. And that might get a whole heap of other people interested because their problems are hard. They're working on a hard problem. So I don't know. This is sort of tantalizing that there must be a whole host of things out there that are physics problems that live in this computational complexity.
So this unitary would be somehow relates to the molecules.
Yes. So they have this procedure for how the linearization of the scattering occurs and how you transform that into this unitary that you described for this network. So, yeah.
The point is when they try to simulate the spectra on a classical machine, they can't.
Yeah. But this has this proof if this works, because this is slightly different. This has these Gaussian state inputs and Fock state detections. So there's this modulo all this stuff. But okay, so that's the end. So what I showed you, our result was that boson sampling with the parametric down conversion sources is hard, but from thermal states is easy and has non-trivial computer science applications. So, one thing I'd like to put on the to-do list, and I don't know, there's been a few good answers at this conference here. Let's say you do the experiment. You vastly exceed what a classical computer can do by some measure of what a classical computer can do, and you're going to write a Nature paper. But you can't sort of do a full verification of the output. What are you going to put in your paper? Like you get 50 photons into thousands of modes. You get the odd click here and there. Is that enough? Who knows? So let me just continue and we can see how we go. Does it have any useful applications? And apparently some people don't think physics is useful, like I just tried to explain to you guys. Everyone sort of nodded. But apparently some people don't like that. How far can sampling algorithms take us? So far, sampling algorithms seem to be the strongest proof we have, like real proof about the hardness of quantum computing. How far can they take us? And there's also fundamental physics questions that come out of this naturally. So, thank you very much for listening, and yes, thanks.
We had a lot of questions already, but
Yes.
maybe a quick one. All right,
No.
okay.
Only really, really long ones.
Okay, let's conclude, and please join me to thank all the speakers for this session. Yeah.